All right, so let's continue our discussion of Chapter 11, Part 2.2 with inter versus intramolecular forces. So intermolecular forces are between particles, and intramolecular forces are the ones that are inside the particle. So for example, in an H2O molecule that I have drawn right here, you can see that the dashes right here are the covalent bonds, and these are the intramolecular forces right here, right here, right here. These ones have a bond enthalpy of about 450 kilojoules per mole or so. And those ones stick together really well. But from one water molecule to the other water molecule, there's also an attractive force. And I've got it highlighted right here, and there's a little dash. This is called an intermolecular force because it's between two molecules, and that would probably have a force of about 10 to 15 kilojoules per mole. So notice how much smaller it is in terms of force. And yet it's very important because when you change phases, go from solid to liquid to gas, this is the part that separates, not these covalent bonds right here. I mean, water is the same whether it's an ice cube, liquid water, or water vapor. It's still H2O. It's just that these intermolecular forces have been broken between solid, liquid, and gaseous phase. The force that changes during a phase change is the intermolecular force. All right, there are three intermolecular forces that we're going to talk about and highlight in this video. And then we'll go in great depth about them next. First are called London dispersion forces, symbolized LDF, or sometimes they're just called dispersion forces, or sometimes you'll even hear them called London forces. They're in all things. They occur because of instantaneous dipole polarization, or instantaneous polarization of electrons. At one instance, the electrons might build up in one area of the molecule, and in the next instant, they might build up in another area. And you can see this example right here in these atoms, where we might have electrons built up in these areas, and then in the next instant, we might have electrons built up over here on this side, and they might attract to the nucleus of this one. And that electrostatic attraction at that instant might be a London dispersion force that takes place. All right, that's an example of a London dispersion force, and it happens in all things, and they're usually the weakest kind. Unless you have lots and lots of electrons, then they can be very, very strong. The next kind are called dipole-dipole forces. Dipole forces happen only between polar molecules, so molecules that have dipoles. So for example, these molecules right here have a positive and a negative end to them. And so they'll stick together with one another, where the negative end attracts to the positive here. The positive end right here attracts to a negative end right here. And so these portions, these little red lines here, are the intermolecular forces that are called dipole-dipole forces. They're positive and negative parts of a molecule that are attracted to one another, and generally they're stronger than the London dispersion forces or the dispersion forces. Generally they are. Like I said before, if you have lots and lots of electrons in something, the dispersion forces can be really strong too. But for the most part, dipole-dipole forces are stronger. And lastly, there's a special type of dipole-dipole force called a hydrogen force, or it's commonly called a hydrogen bond. It's not a bond right here like this. It's a bond that occurs molecules that have an H connected to an FO or N inside of the particle. Notice it has to be an H connected to a phone, one of those three. And it's an interaction of the hydrogen atom with a highly polarized or a highly electronegative atom of fluorine, oxygen, or nitrogen. This causes the molecule to have a real high positive negative part to that particle, and then it causes it usually to stick together better. Water is actually one of those substances that undergoes this hydrogen force. The oxygen atom pulls the hydrogen atom's electron really close to itself, exposing the nucleus of the hydrogen atom right here. Since it only has one electron, it would just be a proton right here, and that's highly attractive to these electrons right here. It only happens, though, when hydrogen is connected to F, O, or N, and so that can be a clue all the time that you want to look for things that have F, O, or N in them. And you can see some examples of hydrogen bonds here between water and water, between hydrogen fluoride and hydrogen fluoride, between ammonia molecules right here, because H right here is connected to an F, O, or N, and then it connects to another molecule where that's happening. Or water molecules, once again, attracting to something else on an ammonia molecule right here that has H is connected to F, O, or N. Here's another example of it right here, just looking from the opposite direction, and how the exposed nucleus of the hydrogen will connect to that electronegative atom in another molecule. More on all three of these types right here in great detail in the next few videos.